Hello, Caymans, Mr. Eicher here. I'm going to be teaching you a lesson about angles and angle measures. This is Chapter 11, Section 2. What you see on your screen right now are some review questions from yesterday's lesson, 11.1, about right triangle trigonometry and SOHCAHTOA. So I thought it would be helpful to review those with you and also review special right triangle patterns. So let's get started. First triangle we have here says find values of the 6 trig functions. The 6 trig functions, we have sine of an angle, cosine of an angle, tangent of an angle, and then we have cosecant of an angle, the reciprocal of sine, secant, the reciprocal of cosine, and then cotangent, the reciprocal of tangent. So those are the 6 things that we need to identify. So each one will probably have a fraction. So it would be a good idea to note where our angle is. The angle that we are basing our answers on is this angle theta, Greek letter theta, also known as angle B. We're going to need the hypotenuse. The hypotenuse is the longest side of the triangle. Be careful here, you might think it's a 4, 3, 4, 5, but actually the hypotenuse should be the longest side. So if this is a 3, 4, 5 triangle, the 5 should be on that side AB. So to find that side length, we're going to have to do the Pythagorean theorem. 3 squared plus 5 squared equals this length C squared. So that's 9 plus 25 is 34 is C squared. So C is the square root of 34. So a little bit bigger than 5, maybe close to 6 is the square root of 34. So to identify our angles, we would have sine of theta. The sine ratio is defined as opposite divided by hypotenuse. That's the SO of SOHCAHTOA. So opposite of angle theta is over there, and the hypotenuse we just found, so that would be 3 divided by the square root of 34. Now, technically, we should rationalize the denominator by multiplying the top and the bottom by the square root of 34. So when we do that, a better answer would be 3 root 34 over 34. So this is our first ratio for sine of theta equals 3 root 34 divided by 34. I'd encourage you to pause the video and see if you can find the other 5 trig ratios. Go ahead and pause the video. The answer is coming up very soon. So in blue we have the 3 famous trig ratios from SOHCAHTOA. The cosine is defined as the adjacent side divided by the hypotenuse, and then tangent of an angle is defined as opposite over adjacent. And now the last 3 I'll do in red, and those answers are right there. Cosecant is the reciprocal of sine, so all I did was do a reciprocal of this to get this answer. Secant is the reciprocal of cosine, so all I did was flip that answer. And then cotangent is the reciprocal of tangent, so 3/5, and that would be 5/3. So that's a little review of the 6 trig functions. Let's now look at our special right triangle patterns. These right triangle patterns will be really helpful in a later lesson. Also, these patterns occur on the PSAT, the SAT, the ACT, and Math 4, and AP Calculus, and higher level math. These are really, really special triangles, a lot of applications. So there's a couple ways that we can illustrate that. If you know the pattern, go ahead and pause the video and fill in both of those patterns. But one way to write the pattern is if this side is a length of n and this side is a length of n, these would be congruent sides. They're congruent because the angles opposite of those sides are the same. This is an isosceles right triangle. It's called isosceles right triangle. Now, if you forget the pattern, you could use the Pythagorean theorem to find what the hypotenuse is. That would be n squared plus n squared equals whatever that hypotenuse squared is. That would be 2n squared equals what we're looking for, square root both sides, and we get n times the square root of 2. So that's the pattern for a 45, 45, 90 triangle. The pattern for a 30, 60, 90 triangle, let's label the angles. Looks like the 90 is already labeled for us. The smaller of the two look like this one. The middle sized angle is this one. So with our 30, 60, 90, we base everything off of the side opposite of the smallest angle, 30. So the side opposite of that is this side, opposite of the angle. The angle's looking towards that side. And we base everything off of that length, which we call length n. And if that side is n, then the hypotenuse is double that, 2n. Now, if you don't remember the pattern for the third side, the middle length side opposite of 60, you could use the Pythagorean theorem to find that. That would be n squared plus something squared, I forget what it is, equals 2n squared, Pythagorean theorem. So my something squared is going to be 4n squared, and then subtract n squared from both sides, 3n squared, square root that, and that's my something. We can take a square root of n squared, so that would be n root 3 is my question mark there. So this pattern is for a 30, 60, 90 triangle. So that's a little bit of review of some things that you've seen before. And then lastly, I'd like to do a review on actually using these trig ratios to find some things. So in the first question, we're looking to solve for the angle theta, which is right in here. We're given this 4, which is opposite of angle theta. And we're given 13, which is the adjacent side to angle theta. The right angle tells me that this side is the hypotenuse. So we're told information about the opposite side and the adjacent side. So an O and an A. That should let you know what trig ratio, sine, cosine, or tangent you need to use. You would need to use tangent. So we would write it as tangent theta equals opposite length, 4, divided by the adjacent length, 13. To solve for theta, we do an inverse operation to get rid of tangent. Tangent is an operation acting on theta. And there's 2 different ways that you can write it. It'd be nice for you to know both ways. One way you can think of it is theta is the inverse of tangent. So a tangent with a little -1, that's what the button looks like on your calculator. A little -1 right there. So if we did that, we would do secant on my calculator, tangent, 4 over 13. So it looks like our angle is 17.1 degrees. It says round angles to the nearest tenth, and that is the nearest tenth for that angle. Let's say you did this and you got this answer, 0.2985. Where in the world did that come from? That's not the right answer. The problem is on your calculator, the mode is not set to degree mode. So if you click mode, your calculator is probably set on radian mode, which we'll actually talk about later in this lesson. You shouldn't be set in radian, it should be set in degree mode. And then you would get the correct answer in terms of degrees. Let's look at another example review question. In this next triangle, we are solving for this side. We're provided this angle of 41 degrees, and we know that the side opposite of 41 is 4, and the side that we're looking for here is the adjacent side to 41. Again, we don't know the hypotenuse, so whatever trig ratio we use, we'll need to have an adjacent side and an opposite side and an angle. And that would be TOA again, SOHCAHTOA. TOA, tangent is opposite over adjacent. So we can set this up as tangent of 41 degrees equals the opposite side divided by the adjacent side. Now, we have a variable in the denominator x. We can multiply both sides by x. Multiply it over here. That gets rid of the x. And then we could divide both sides by tangent of 41. So in your calculator, when you're in degree mode, you would have 4 divided by tangent 41. So I get x is 24. That doesn't make sense. I must be in radian mode. There we go. I get 4.6. That makes better sense with the diagram. And we asked around to the nearest thousandth. This place here is the nearest thousandth place. The last one has a little heart by it. I like the little heart. I'd like you to try that. You can try it right now if you'd like. But that's a question that you'll see be on the Try This 11.2. That's the first part of the video. That's all review, nothing brand new there. And the next part of the video, we will talk about some new content about angles and standard position and some other terms. Thanks for watching this video. See you next time.